Now, what we noticed is that not every vector field satisfies that conservation law. So if you have a vector field like this, basically you imagine a circle and the forces act along the circle at every point, so that all these forces are tangential and go in the same direction. Well, then moving a particle along such a path will generate some positive work of the field of forces, and therefore in this case we do not expect any function, any energy function, such that the vector field is the gradient. So let's look quickly at why is it that we should not expect any function. Is it possible to have a function such that its gradient looks like this? So what does it mean that we have these vectors, the gradient vectors of some function? So we have this plane being the domain of the function, right? And then if you think of three-dimensional space and the graph of the function, the surface in that space, then what does it mean that this vector is a gradient of that function? It means that moving in that direction increases the function the fastest way, right? That's the meaning of gradient. So that means that as we move in that direction, the function increases. And then at the next point, we move further and it decreases again. And it increases again. But as we come back to the initial point, we expect to have the same value of the function. So it is impossible for the gradient of any function to have a path like this. When you increase the value of the function, increase your altitude all the time, and then you come back and have the same altitude. That's the basic reason why it's impossible to have such a function. Well, speaking in terms of just functions mathematically.